Welcome back. This is part 4 in this series of things around Bayesian regression and inference. Interestingly, I had not planned to make a video about this topic, but while preparing the material and tutorial on the next topic, which is about applying the proper Bayesian treatment, I felt it is very important to have a good intuition. As well, the practice to apply these so-called rules of probability. If you are already well versed with the notion of joint, marginal, and conditional probabilities, and more importantly, you know how to compute them, then you should skip this tutorial. The content of this tutorial and the example used is based on the chapter 1 of the book by Dr. Bishop. I start with a brief description of the problems we will end up solving after learning the required concepts and techniques. Essentially, we have here two buckets with fruits in them. One bucket is of color red and the other is blue. The fruits are of two types, orange and apple. And we will answer two questions towards the end of this tutorial. The first one is to compute the probability of selecting an apple. And the second is to get the conditional probability of blue bucket given we have picked an orange. In this problem setup, we have two random variables. Bucket is a random variable that has colors as it states, and fruit is also a random variable that can be either an apple or an orange. For now, we set aside the problem itself and learn the concepts using general notations and symbols. For that, I have two random variables, x and y, that define our phenomena or process. In other words, both x and y are required for a process to happen. In this process, x can attain one of 5 different states and y can have one of 3 states. Essentially, it's a discrete random variable. Now, as part of our experiment, we record the various combination of these states that these two random variables can take. In order to do so, we create a table and perform our observations n times, or we say that we have n as the number of trials. We then record how many times a certain combination of states out of n times happened. The little n with subscript in the table indicate the count or number of times the combination of state happened. For example, the number of times you observed the combination x4 and y2 is indicated using n42, the orange colored entry. So one obvious question of interest for us is to know the probability of random variable x being x4 and random variable y being y2. Remember, the process can happen only when we have the states for both of these random variables. Since this will essentially be the relative frequency of this combination, we can compute it by dividing n42 by n. Of course, our assurances of this probability hinges a lot on the size of n. The bigger the n, more we can be sure of the relative frequencies. For the purpose of this tutorial, assume our experiment indeed ran for sufficient number of trials. This probability of state, like this, is known as joint probability. We ask a different question, and it is about finding the probability of x being in state x4. As I said earlier, the most important thing to appreciate here is that x cannot occur in isolation because the process is about both x and y. So x will always have y because that's the only way our process comes to life, when both are present. Now, x will be in the state x4 in combination with y1 or y2 or y3, indicated using the relative the counts that you see in the grid. So we must now take those occurrences into consideration as well. So the relative frequency now will be the sum or total of these observation counts. This is called marginal probability. Note that the notation, that is the probability x equals to x4, here is not very helpful. It does not anywhere indicate the fact that there are other random variables involved. Similarly, we could have been interested in the marginal probability of y. For example, if we were interested in marginal probability of y being in state y2, then we would add up all the combinations where it occurs. This means that we are adding the entire row this time. So why is it called marginal? It's because traditionally for these kind of probabilities where you are interested only in the state of one random variable, people used to write them on the margins of the table. I have indicated the margins using the orange braces. And you would write it like this. And therefore it is called marginal probabilities. Quite frankly, it's silly. Here is another view. Essentially, we are now using the variables C and R, where C is the column and R is the row. This will help us generalize based on the results we have obtained so far for the state x4 and y2. We can say that for marginal probability of x4, we are summing the entries in the column 4, and for the marginal probability of y2, we are summing the entries in row 2. Therefore, we can generalize all this by indexing our states using indices I and j. Note, now we have a more generic formulation of joint probability. The marginal probability also uses a more generic formulation using the column numbers, where C subscript is the sum of all the states in which state xi appears. The states of random variable y are indexed using j. The same argument goes for marginal probability of random variable y. Here we are simply adding the entries in row j. Now I will perform some substitutions and rearrangements to arrive at more general formulation of marginal probability. First, we know that Ci can be expressed as sum of the entries. So if I put it in our equation of the marginal probability, it would look like this. Now, if you look at the joint probability at the top of the screen, we can see that Nij can be seen as the product of n, or capital N, and the joint probability of x and y. So here, if I substitute Nij with that, it would look like this. Clearly, the capital N in the numerator and denominator will cancel each other, giving us a very generic formulation of marginal probability of state of random variable. This is known as sum rule of probability. In other words, if you want to find out the marginal probability, you apply sum rule. This is for discrete random variable. For continuous random variables, you will use an integral instead of a summation. Here is our original grid and elements once again. Now we will talk about another interesting probability called conditional probability. As the name implies, this time we are interested in getting the conditional probability of y2 given x4. And this is equal to the number of times we observe the combination x4 and y2 divided by the number of times all state x4 occurred, irrespective of the state of random variable y, which is nothing but the sum of entries in the column 4. Very similar to what I showed you earlier, the generic formulation using the indices I and j for the state of random variables x and y would look like this. We will now do again the substitutions and rearrangements to get another more generic formulation. This time I am going to write joint probability in a bit different manner. As you can see that I have somehow injected Ci in here. And because of that, I can now express the joint probability as the product of conditional probability and marginal probability, because these fractions Nij over Ci, that's nothing but a conditional probability, you can see there, and Ci over n is a marginal probability. Hence, this formulation is also called product rule of probability. So essentially, if you are interested in finding the joint probability of two random variables or more random variables as such, then you could see them as the product of conditional and marginal probabilities. Here is the summary of sum and product rules with slightly different notations. These notations appear in the book as well as in many articles on web. In the sum rule, the subscript of the summation symbol has y. It means that we are summing the entries for all the states of y. Similarly, the marginal probability of y can be written like this. The notation now will have x in the subscript of the summation symbol. For the product rule, here is another way to write it. In this formulation, the one in orange, I have a product of conditional probability of x given y and marginal probability of y. Now the product rule has something very interesting going on. You see that the same joint probability of x and y is written using two different ways. Just because I have changed the order of x and y in the second equation does not mean that the joint probability itself will change. And based on this claim of mine, we can write this equation, which means that we can substitute the left hand side and right hand side as following, which means I can express conditional probability of y given x using this formulation of right hand side. By the way, based on the similar arguments, we can isolate the conditional probability of x given y on the left hand side as well. And this, my friend, is nothing but the Bayes rule. It's amazing how simple its derivation is, especially when this Bayes rule is the one that plays the central role in our probability driven modeling in Bayesian statistics. Well, this is why it is called Bayesian statistics. Now that we have learned all these rules and the kind of probabilities they help us get, let's answer our questions. The first task is to determine the probability of selecting an apple. It is given to us the probability of selecting red and blue buckets. Essentially, someone observed it and has provided those probabilities. So the probability of red bucket is 0.4 and the blue bucket is 0.6. Given what we see in the buckets, we can compute the conditional probabilities. For example, looking at the red bucket where there are total 8 fruits, we can say that the conditional probability of fruit being apple given red bucket is 2 over 8 or 1 by 4. Similar argument goes for the conditional probability of fruit being apple given blue bucket is 3 over 4. Now our task as such translates into computing the marginal probability of fruit being an apple. We don't care which bucket it came from. So what rule should we apply here? Since it's a marginal probability computation, we would apply the sum rule. This way we can sum over the other random variable. The other random variable in this case being the bucket random variable. Since there are only 2 states, I have expanded the summation notation as this. As you can appreciate that we have the marginal probabilities of buckets and conditional probabilities, but we do not have the joint probabilities. So in order to compute the marginal, we need to find the values of these 2 terms that are appearing, but we do not have them. And this is where we will be a little crafty and we will use our knowledge of seeing the joint probability as the product of conditional and marginal probabilities. Now we have all the values that we want to use. So it's just a simple calculation now. And this gives us the probability of 11 over 20. We can also say that the marginal probability of fruit being orange is nothing but 1 minus p of or 1 minus marginal probability of A. Since we have only 2 states, this is just a simple calculation now. For this next task, we are asking the conditional probability. Now, whenever you see conditional probability, you should immediately start to think of Bayes rule. This is where we will apply it. Fortunately, in this case, we know all the values or the components that are appearing in the Bayes rule, and some of them we even calculated in our last task, and it amounts to 1 over 3. Here is the summary of all these rules, and this brings us to the end of our tutorial. What is interesting about Bayesian view of machine learning and statistics is that the foundational rules are quite simple, and most of the time we are really applying them to our problem formulations and getting the answers out by the smart and crafty substitutions and manipulations. I hope this tutorial was helpful. Most likely it was a refresher for quite many of you. Let me know if you have feedback and questions and comments. Bye for now and see you in the next tutorial. Bye bye.